Hi everyone, let's take a look at topic set 8 for Chem 11, and this is question number 12, and this is about drawing Lewis structures for compounds that violate or don't follow the octet rule. Okay, so just a quick reminder, there's sort of three of these types of exceptions that you might see. You might see an exception where you have fewer than 8 electrons, and typically that would happen for elements that contain beryllium where 4 electrons can be found, and boron where 6 electrons can be found for those elements and they're still stable. Then you have molecules where they have more than 8 electron, and this could occur for elements on the third period or beyond. And the reason is because when you have n equals 3 or the third shell, your orbitals can be 3s, 3p, and 3d in theory, and up to the noble gas you just fill in up to the 3p orbital, so you really have empty 3d orbitals that could be used for filling in more electrons, which means that bonding is possible for those elements. And since you already have 2 electrons in the s and 6 electrons in the p, you already have 8 electrons. So if you add some more, then you're going to have more than 8 electrons. So anything on the third period or beyond would be candidates for having more than 8 electrons. And then of course the last one is radical species or odd electron species, and we cannot use Lewis structure to draw these molecules or these species, but they do exist. In the particular example that we're looking at right now, SF6, ClF5, and XeF4, they're all examples of number 2 here, which is the ones with more than 8 electrons. I'm going to just draw them and show you how to do this. So let's start with SF6. Just like any Lewis structure, we're going to be calculating the valence electron first to start. And so that's 6 for sulfur, and then there's 6 fluorine. Each fluorine is 7, so we end up with 48 electrons. You'll just start with sulfur in the middle, and then you would put your skeletal structure, which has 6 fluorines around it. And immediately you can tell that the sulfur in this case would violate the octet rule because it has 12 electrons total, but sulfur is located in the third period. So as a result, we accept that it could violate the octet rule. And then so the remaining step is really to figure out if we can place all the 48 electrons in this structure. So each fluorine requires 8 electrons. So fluorine is on the second period, so it cannot violate the octet rule. So it has to have 8. Okay, so I'm going to do 8 for all the fluorine, which just means 3 more pairs of electrons. And if you calculate how many electrons you have now, there's 4 per each of these fluorines. There's 6 of them. 6 times 4 is 24. That's pairs, so that means there's 48 electrons. Okay, let's take a look at the second one, ClF5. Calculating valence electron, this gives us 7 plus 5 times 7, so a total of 42 electrons. Cl is less electronegative, so it'll be in the middle, and we can draw our skeletal structure looking like this. And again, you can see in this case the chlorine atom immediately violates the octet rule with having 10 electrons, but looking back in the periodic table, chlorine is in period 3, so again it could violate the octet rule since it has that empty 3d orbital. So right now, just completing the structure, we would put 3 around each fluorine to make it 8 total with the bond 2 chlorine. And so now if we count, we have 4 pairs of electron around each fluorine times 5, that's 20, right? 20 means 40 electrons. Since we have 42, we need another pair, and that last pair should be on the chlorine itself. So the chlorine can violate the octet rule, but the fluorine cannot, right? So the F cannot violate, but the Cl can. So that's why we draw it that way. Our last structure is xenon tetrafluoride. The valence electron here is 8 plus 4 times 7 equals to 36 electron. Xenon tetrafluoride with xenon in the middle, the 4 fluorines around, and then putting octet for each fluorine. Now we have 4 times 4, we've used up 16 pairs or 32 electrons, and we still have 4 electrons left. The only place you can put those 4 electrons would be around the xenon, because xenon is pretty low in the periodic table. It has those additional empty orbitals on that shell that could be filled with electrons. And this is actually a really good example, xenon tetrafluoride, of the idea that the larger noble gases, as you can see here, are actually able to react with other elements to form compounds. The smaller noble gases cannot, because the smaller noble gases, for example helium or neon, really has that particular shell completely filled. So helium is 1s2, neon is 1s2, 2s2, 2p6. So for those particular shell, the first and the second shells, they are full with that configuration. But once you go to the third one, fourth one, fifth one, etc., you start having those d orbitals and f orbitals, and they're the ones who can accommodate this extra electrons. And so the larger noble gases now can actually form compounds. Okay?